In the previous lecture, we were able to determine the relationship between electric fields and the electric potential difference. So now we're going to apply our result. Let's suppose we have a solid conducting sphere that has a total charge given by positive Q. Now our solid sphere is a conductor, and that basically means all the charge will lie on the surface of our sphere. So the charge is distributed uniformly and evenly on the surface of our conducting solid sphere, as shown by the following positive signs. Now the radius of the sphere is R0, and notice that the electric fields begin on our surface and extend outward, as shown by the following vector. So these are the electric field lines. Now, we would like to calculate the electric potential, also known as the voltage, of a conducting solid sphere at distances greater than the radius, equal to the radius, and less than our radius. So let's begin with part A. So before we give the electric potential, we have to find the electric potential difference. We have to calculate the voltage difference. Now, in the previous lecture, we were able to show that the voltage difference between any 2 points A and B is equal to the negative of the integral of the dot product of EdL from point A to point B. So, let's choose any 2 points outside of our conducting solid sphere. Let's suppose point A is found here and is a distance RA from the center of the sphere, and point B is found a distance RB from the center of that same sphere. And these 2 points lie on the same exact horizontal axis. Now, to calculate our voltage difference, we have to use this equation. Now, by definition of the dot product, we know that dot product is equal to the product of the magnitude of E multiplied by the magnitude of DL multiplied by the cosine of the angle between these two vectors. Notice that our electric field vector and the DL vector point in the same exact direction. So the angle is 0. And cosine of the angle 0 is 1. So this simply becomes the following quantity. So the electric potential difference between point A and B is equal to negative of the integral EdL from A to point B. Now, in a previous lecture, we were able to show that the electric field at points outside of a conducting solid sphere is given by this equation. So the electric field is equal to Q divided by 4 pi multiplied by epsilon naught multiplied by R squared, where R is the distance from the center of our solid sphere. So we replace this E with this quantity and we get the following result. So the voltage difference between point A and B is equal to negative of the integral. We also replace our DL with DR, and we replace A and B with RA and RB. Now, we take our constants and we bring our constants outside of our integral. So Q is a constant, 4 pi, and epsilon naught are also constants. So we get the following result. And now we integrate the following, and then we evaluate that integral from RA to RB. And we get the following result. So notice this is the voltage difference. It's the electric potential difference between any 2 points A and B outside of our solid conducting sphere. Now, what we want to calculate is the electric potential, or simply the voltage. So let's make the assumption that when our RB approaches infinity, when this point is somewhere very, very far away, in fact, infinitely far away, our voltage at that point is assumed to be 0. So that basically means this quantity goes to 0, or this quantity goes to 0, and we're left with the following result. The voltage at point A as a result of this conducting solid sphere is equal to Q divided by 4 pi epsilon naught multiplied by 1 divided by R. Now, let's move on to part B. Now, let's suppose our R is equal to R naught. So, to calculate the electric potential or the voltage at R equals R naught, we simply take this equation and plug in R naught for our R. And we get this result. So, the voltage on the surface of our solid conducting sphere is equal to Q divided by 4 pi multiplied by epsilon naught multiplied by 1 divided by R naught. So this is the voltage on the surface as long as we assume that at an infinitely far distance away, the voltage is 0. So, let's move on to part C. What is the voltage difference inside our solid sphere? Now, inside our sphere, we have no charge. So that means our electric field inside is 0. And that's because all the charge collects on the surface. So that basically implies that this quantity, our potential difference, our voltage difference, is equal to 0. And that means there is no voltage difference inside our conducting sphere between any 2 points A and B inside. Now, that basically means that the voltage inside the conducting sphere is constant and it's equal to the voltage at the surface. So the electric potential or the voltage inside our conducting solid sphere is simply given by the equation that we were able to show in part B.